Hello, my name is Anirudha. I'm a second-year PhD student from Princeton. On behalf of my colleagues, I would like to present our work in providing generalization guarantees for imitation learning. The question we want to address is how can we guarantee that with imitation learning, the robot will succeed with high probability in a new environment? For example, how can we guarantee that a manipulation strategy trained on a dataset of objects will generalize to novel objects? How can navigation policy trained on a dataset of rooms generalize to novel rooms? Here we're looking at nonlinear hybrid dynamics and rich sensing, such as pushing a block with real-time visual feedback. The idea is to leverage the probability approximately correct Bayes generalization theory that can provide such guarantees. Imitation learning has been a popular tool to accelerate control policy training by injecting expert knowledge. However, imitation-based policies can fail to generalize to novel environments, either because the expert behavior is not safe, or because the algorithm fails when the robot encounters unseen states. Currently, there's no rigorous generalization guarantee for imitation learning. Meanwhile, the PAC Bayes Control Framework has been recently proposed to provide guarantees for control policies. The main result is, with high probability, the true expected cost of the policies in testing environments can be bounded by the training cost and the regularizer. Here we assume there's an unknown distribution D over environment. Our overall approach is to first learn a prior policy distribution P0 by imitating expert demonstrations, and then fine-tune it using training environments S and obtain the posterior distribution P and the associated generalization bound. For the first phase, we assume we have collected a diverse set of expert demonstrations, and then we use a conditional variational autoencoder to embed the multi-modal expert behavior into the latent distribution P0. The decoder, or the policy, is conditioned on the latent variable Z. Looking at the CVA closely, we embed the whole trajectory of observation and action of each demonstration into a single latent variable Z. At the end, we obtain the optimized decoder policy and the prior latent policy distribution, which is assumed to be uni-Gaussian by the CVA formulation. As example, we can obtain diverse graphs by sampling from the prior as the model imitates diverse demonstrations. Next, we fine-tune the prior by optimizing the generalization bound. The policy from phase 1 is reused with its parameters fixed. We also use a new set of training environments. As a reminder, we're minimizing the bound CPAC, which consists of the cost of training environment and the regularizer. Since we obtain the cost for each training environment using black box simulation, we use evolutionary strategies to approximate the gradient. The result of this phase is the posterior latent policy distribution and the associated generalization bound. This means the expected success rate over all testing environments using policies from P is guaranteed to be at least 1 minus the bound. We demonstrate the effectiveness of our approach on 3 robotic tasks. The first one is to grasp diverse marks. We also transfer the policy training simulation to hardware in 0 shot. Through training, we get a 93% bound on success, and the estimated test success rate is 98.4%. The next example is planar pushing using external vision feedback. The goal is to push the block across the table. The image on the right shows the start and end regions for 2 tasks with different difficulties. The bound is 90.4% for the easy task and 81.0% for the hard task. The last example is indoor navigation with onboard vision feedback. The goal is to navigate through a home environment with randomly placed furniture to reach a target region. The bound is 74.1% and the estimated task success rate is 79.9%. Here, we show the trajectories sampled from the multi-modal prior and the fine-tuned posterior. Although our approach does not necessarily produce diverse trajectories at the end, we find that our model exploits the multimodality of the expert demonstrations to accelerate fine-tuning and help posterior achieve better empirical performance. As a summary, our work is able to provide rigorous generalization guarantees for imitation-based policies in novel environments using multimodal demonstrations, latent condition policies, and the PAC Bayes Control Framework. We demonstrated the effectiveness of our approach in manipulation and indoor navigation tasks. Thank you.